going to do kind of your introduction to cosmology today. And basically, cosmology is the study of the entire universe as a whole, its structure, its history, its origins, its fate. It is the biggest picture thing you can try to tackle, okay? It is incredibly hard to do because we are incredibly small, as you've already probably started to realize. When we started looking at the size of the solar system, and then we started thinking about the size of the galaxy, and then you extrapolate that into the size of like the galaxy clusters and even to the size of the universe. It is such an enormous thing to try to understand that we struggle with it. But that is the goal of cosmology. In the IB syllabus, they want you to understand Olber's paradox. We will talk about that. They want you to understand the Big Bang model and why we have this model and this belief that the Big Bang was the creation of the universe and the evolution and development of the universe. So that's our goal. That's our goal. Olber's paradox. Thanks for that commentary. Here's the idea, though. Okay, let's go back to the age of Newton. Newton thought that the universe was stationary, was infinite, and did not change. And that makes some sense if you think about it, because really, when you look outside, the stars appear pretty much the same year after year after year. And so that was his thought. Now, the problem with this is if that is true, this is the paradox, and it's not just some sort of weird mind game. We'll show you mathematically why this is true. But if the universe was infinite, and if it is stationary, and it's uniform in all directions, there should be no darkness. Okay? We should not have nighttime. That is Olber's paradox. Why is the night dark? Because we know it is, but according to this, it shouldn't be. Brian? It would be like staring at the sun in all directions. Okay? We would have evolved. Oh boy, this thing's giving me trouble. So here's the paradox. Here's the reason why this is true. Think about it for a second. If we know that light from objects gets weaker with the square of the distance. It's an inverse square law. If something is twice as far away and it's luminous, it'll appear 1/4 as bright. Right? We talked about kind of the brightness-distance relationship. So technically, you should be thinking, well, that makes sense. Like if things are farther away, they should be dimmer. However, if you think of us being in the middle of a sphere, as that sphere gets bigger and bigger, the surface area that it contains grows with the square of the distance. So twice as far away, and the surface area of the sphere that I'm looking out onto has gotten 4 times larger. And therefore, there should be 4 times as many stars in a given area, right? So if the universe is uniform, even though the light from objects would diminish with the square of the distance, the number of stars I see should increase with the square of the distance. And those should cancel each other out. And therefore, in every direction I look, there should be light coming from some object. And we know that's not happening. So that's the paradox. We need to figure out why that's not happening. Okay? So by the end of this PowerPoint, my hope is we'll have some solutions as to why Olber's paradox is no longer a paradox. Okay, but first, we're going to move on to Edwin Hubble. Famous astronomer, got a telescope named after him, pretty darn good telescope too, okay? And we know already, we've talked about this before, but in the 1920s, in 1923, he discovered a Cepheid variable in the Andromeda Nebula. Please remember that this is less than 100 years ago, okay? Which I know at your age seems like a long time, but you know that was about when I was born, and so it's not that long ago, right? And less than 100 years ago, galaxies didn't exist. Okay? We had stars, we had planets, we had nebula, we had comets, and we had these fuzzy things. And pretty much any fuzzy thing was a nebula. And we didn't know if it was actually a nebula or what. Well, this Andromeda Nebula, when he found that Cepheid variable, remember a Cepheid variable was a good standard candle, he was able to prove using that it was much farther away than anything else we had seen, and therefore it wasn't part of our galaxy. It was a separate galaxy in and of itself. He called it an island universe. That was the first discovery of galaxies, and suddenly our universe got much larger. And we keep making discoveries like that and making things, expanding the size of our universe. He found it to be about 2.2 million light years away, okay? And this was the first solid piece of evidence that these things that we were calling nebula, some of them were actually entire galaxies. Okay, Jonathan?
Does it appear, at least with our knowledge now, that...
Okay. So with this proof that galaxies actually existed, then there became more investigation, and it turns out there's different types of galaxies. And IB would like you to recognize 3 general categories of galaxies, okay? The 3 general categories of galaxies, one of them is what's called a spiral. We live in one. We call it the Milky Way. The Andromeda galaxy is also spiral. There is new evidence that came out just this past year that we think maybe we live in what's called a barred spiral galaxy, which would still be a spiral galaxy, but it would have more of a bar of stars running through the middle and spiral arms coming off of it. It's hard to tell exactly what we live in because we're in it, you know what I mean? But that was some evidence that came out that way. But spiral galaxies seem to be pretty common. They tend to be flat, spiral arms, they rotate, okay? The second category is elliptical, and these are kind of unusual ones. They don't have arms. They can be anywhere from like a giant sphere down to like just a flat, mushy pancake without the spiral arms, okay? And these tend to be the largest galaxies we see with the most numbers of stars in them. Rachel. And the third type of galaxy is known as just an irregular galaxy. These are the strange ones. The large and small Magellanic Clouds, they don't really have structure to them. There's other galaxies that are really irregular because they've either collided with another galaxy and been ripped apart, and they have these strange shapes to them. So that's just kind of the third class. We will probably be irregular for a while, and then we might settle into some other shape. There does appear to be some kind of an evolution in terms of how galaxies evolve, and it does appear that galaxies actually oftentimes do collide and merge and become one larger galaxy, and that's kind of a natural, it seems to be maybe a natural process. If you study galaxies further, there's many, many subcategories in these large categories. There's different types of spirals, there's different types of ellipticals. You don't need to know the specifics of those. But here's a picture with a few galaxies just to give you an idea of like different shapes, different sizes. And if you're interested in galaxies, there's actually this website called Galaxy Zoo. And you can actually become a galaxy researcher. With the technology we have now, there are so many images of galaxies that we can't keep up with them and actually catalog them all. And they're having citizen scientists, people like you, do this. And you can go to Galaxy Zoo and you can figure out how to do it, and you can actually start like observing galaxies and cataloging them. And sometimes you make a discovery. There's a woman in England that now has a new phenomenon named after her. It's like the Betty phenomenon or something, because yeah, exactly, that green cloud thing. So let's try to get a little bit of a grasp of kind of the relative sizes of things that we've been talking about. Just again to kind of go back, this is a horrible picture, but it's not drawn to scale, but it should give you an idea of what we're talking about, okay? This is us here on the Earth, okay? We are but one planet going around one average-sized star, which we call the sun. There are other planets you can debate if there's 8 or 9, and there's asteroids, and there's meteors, and there's comets. We all go around, so that's called our solar system. Our solar system is but one average star in this conglomeration of stars and planets and nebula and other things that we call a galaxy. The Milky Way galaxy, we think, has somewhere between 200 and 400 billion stars in it, okay? And we are out here on one of the spiral arms. That's somewhere between 2 and 400 billion stars. That's a big source of error. Remember uncertainty, you know. 2
billion or 200?
200 to 400 billion, yes, okay? Somewhere in that range. It turns out the galaxies appear to be clustered together. We live in a cluster of about 24 galaxies that's called the local group. Pretty exciting name, the local group. There's another cluster that we see when we look at the constellation Virgo. If we look beyond Virgo, there's a cluster of many, many other galaxies called the Virgo cluster. So galaxies appear to have these clusters shapes, and the clusters tend to be organized in these things called superclusters, okay? And they kind of make this kind of filamentous network throughout the entire universe. And it appears that there are hundreds of billions of galaxies out there. I mean, with the Hubble, we found many more galaxies than we previously thought existed. So as our technology increases, we keep finding more and more and more stuff. So that's kind of an idea of kind of the layers of the universe. Michael. So while we're talking about galaxies, let's look at this. This is a really cool thing. Okay, if some of you guys went to one of these lectures, the Aspen Center for Physics lectures, they talked about this stuff. But here's the deal. Here's a galaxy. Let's imagine it's a spiral galaxy and it's rotating. You guys know from Kepler's laws, hopefully you know, but maybe you remember. Remember Kepler's laws? He talked about the planetary motion and the fact that basically in our solar system, planets and objects that are close to the sun move faster than objects that are farther from the sun. You with me? And that makes sense in a system where most of the mass is at the center, and the sun is at the center and it's most of the mass. And when you have a system like that, you would expect farther objects to orbit more slowly than near objects. So we look at a galaxy. We see that most of the stuff is in the middle, kind of like our solar system. We would expect, according to Kepler's laws, that the outer stars would be moving more slowly than the inner stars, just like Mercury moves more faster than Pluto, which is not a planet. But anyway, you with me? When we observe galaxies, this is what you would expect. You'd expect diminishing velocities as you moved away from the center. What we observe is not that. We observe that they all tend to rotate at about the same speed, no matter how far from the center they are. This is not okay. This is weird, okay? What this means is that if mass is what exerts gravity, which is what we believe to be true, and we observe most of the mass at the center, but the way things are rotating is not like all the masses at the center, is that there must be mass that we can't see that's not at the center. And we've named that stuff dark matter. Matter, because it's mass, it exerts gravity. We see the gravity here exerting equally all around. But dark, because we can't see it. We don't know what it is. And that's what dark matter is. It was first observed with individual galaxies, that individual galaxies weren't rotating the right way. It's now been observed with galaxy clusters. You can look at entire clusters and see how the galaxies are interacting gravitationally. And the amount of gravitational force needed to make it happen is not nearly, the mass that we see is not nearly enough to create that. Does that make sense?
Like, you know, they account for the mass that they assume.
So dark matter. There's this stuff out there exerting gravity that we don't know what it is. But we can calculate how much of it is compared to what we can see. You know what I mean? And when we just look at this stuff, and the numbers have changed a little bit, but in the book, and what they're talking about is it appears that the matter that we can see is only 10% of what is needed to create the gravity we're measuring. You with me? So 90%, there must be 90% more dark matter, stuff that is not observable to us yet that's exerting gravity. Okay? So when we look at the rotational motion, we start seeing that the gravity the gravity needed to create the motion that we see is much more than what we see. You can either think two things. You can think either there's more mass out there that we can't observe, and we call it dark matter, or gravity's wrong. And those are two viable options. And there are people that are trying to figure out why gravity is wrong, why our understanding of gravity is incorrect, and don't believe that dark matter is the solution. The majority of astrophysicists right now believe that dark matter is the solution, and that there's three possibilities, three general categories of what dark matter might be. Okay? The first one is neutrinos. Okay? There's the halo. First thing that it might be is neutrinos. We know neutrinos exist. Whether or not they have mass or enough mass is still uncertain, though my understanding of the physicists I've talked to is that they've pretty much ruled out neutrinos as dark matter at this point. They've measured neutrinos well enough to know that it's not nearly enough to create the dark matter that's needed. The second category are what are known as machos. Macho stands for massive, compact, halo objects. So the idea behind a macho is that maybe there's a bunch of stuff out here that is massive, let's say like a giant, like a Jupiter, but it's not glowing, so we can't see it. Or a small, it's something that's bigger than a planet but smaller than a star. You know what I mean? Like brown dwarfs. So maybe there's a bunch of stuff out here. They've actually done studies to look for machos. Here's what they did. They took a telescope, they aimed it at a distant galaxy or a distant star. Actually, it had to be out of our galaxy. So they aimed a telescope at a distant galaxy, and they waited. And they figured if there's a bunch of machos out there, every so often one's going to go in front of that distant galaxy, and you'll be able to see it. Right? The galaxy will get dimmer because something will go in front of it. They did this for millions of stars or galaxies. They've done this over and over, and they found some machos, but not nearly enough. Not nearly enough. There are some weird things floating out here, like big old lumps of charcoal floating, but there's not enough of them to make up for dark matter. So WIMPs is kind of the direction physicists are going right now. And that guest lecturer, that was kind of one of the things he was talking about was WIMPs. And WIMPs stands for Weakly Interacting Massive Particle. And the idea is this. Maybe there's a subatomic particle that has mass, so it exerts gravity, but it doesn't interact in any other way very much. It's weakly interacting, so it's very, very hard to detect. And a lot of physicists are looking for WIMPs right now. That's their goal, is to find WIMPs as the answer to the dark matter question. All right, let's talk about waves for a second. We'll kind of a little review of waves. Remember waves last time? You had amplitude, frequency, all that stuff, okay? And in astronomy, you hear about redshift and blue shift all the time. So just a review of that. When something is creating waves and the object is moving away from you, or you're moving away from the object, those waves will be stretched out longer. And since red light is longer than blue light, we're talking about light, we say it's redshifted. You guys all remember this? Totally good stuff? Excellent. Edwin Hubble, not satisfied with the fact that he discovered galaxies. And by the way, there's some debate about whether he was actually the one that found the Cepheid variable or it was one of his assistants, but that's getting into the history of science, which gets kind of crazy. But not only did he discover galaxies, but then he started measuring galaxies, and he started noticing that every galaxy he looked at was redshifted. Everyone he looked at, except for the Andromeda Galaxy, was redshifted. The light from it was redshifted. So he went with the assumption that those galaxies are moving away from us. Therefore, the universe is expanding. This was the first piece of evidence that the universe was expanding. And when this was discovered, this was huge, because prior to 1928, 1929, everyone assumed the universe was static, that it was not moving, that it was stationary. Even Einstein himself, who when he came up with this theory of general relativity, okay, he wrote this equation, or more than one equation, that described gravity very elegantly, very beautifully. But in his equation, in order for it to work, the universe had to either be expanding or contracting. And he went to his friend, it might have even been Edwin Hubble, I can't remember. He went to his friend the astronomer and said, hey, what's the universe doing? Is it expanding? Is it contracting? And they said, sorry, Einstein, it's static, it's stationary. And he's like, ah. And he goes back to his room, and he adds the cosmological constant. This is a famous story. Many of you probably heard it. He added this constant to his equation so that it would work in a static universe. Well, then afterwards, they discovered the universe was expanding. Now, to me, that is amazing, that a mathematical equation can discover that the universe should be moving before we ever have any contemplation that it actually is. That math can predict reality sometimes better than we can. I find that to be really bizarre, personally. Okay, so, sidetrack. So when Hubble discovered that everything was redshifted, it was obvious that then everything's moving away from us, and then, therefore, the universe is expanding. Well, this leads to an interesting question. If the universe is expanding, let's move back in time. Let's say 1 million years ago, the universe must have been smaller. 5 million years ago, it would have been even smaller yet. And it turns out you can rewind the clock, and you can get to a point where the universe actually was at a point. And that is where the idea of the Big Bang comes from, that the universe actually began when there was an explosion is a word we use all the time, but it's really not the right way of thinking about it. It's just a rapid expansion. There was a beginning, okay? There was a beginning. It is no longer infinite in time and space, okay? It might be infinite in space, but it's no longer infinite in time, that there was a beginning. It hasn't been around forever. And that changes our perspective, okay?
Yeah, that's a good
I want to show you some data here because I think it's intriguing. I think it's interesting. And I just added this last night, so I wanted you guys to see this. Here's Hubble's original data. Now, would you see a linear trend in that data? The fact that he saw a linear trend is remarkable, okay? Notice this is going out to about 2 megaparsecs away. Okay, what a parsec is what, 3 light years? So that's like 6 million light years away. Is that right? Did I do my math right? Okay. And what Hubble said is, as these galaxies get farther away, they appear to be receding at a greater rate, and there appears to be a linear relationship. Now, I personally find that an incredibly big stretch. Now, there are some mathematical things he did to refine his data so that the linearity of it became more apparent. But that was a huge discovery. And I want you to see, as the technology got better, and we've measured galaxies farther and farther away, what it looks like now. Okay? When you go out to 500 megaparsecs, all of a sudden, it totally appears extremely linear. But the fact that Hubble was able to recognize that from this, I think, is huge. It's unbelievable. And it, again, another massive change to our understanding of the universe. Okay? So a couple of things come from this, you guys. This is known as Hubble's law now. The farther away an object is, the faster it recedes from us. This is actually a tool. Remember we've talked about measuring distances? This is a tool for measuring very large distances. Because if we know the slope of this line, we can use that. If we can measure the redshift, we can figure out how far away the object is. Because farther away objects will be more redshifted. They'll be moving away more rapidly. And there's actually an equation for it. So here's the two equations that come from Hubble's law. This top one is Hubble's law, V equals hd. And we'll talk a little bit about that because it's helpful for a lot of things. But the second one is this. The change in wavelength of what we observe divided by the wavelength of what it should be. So let's say we look at a galaxy and we look at the spectral line for hydrogen, for ionized hydrogen, okay? And we know what the wavelength of that line should be. That would be in the denominator here. But we observe in a galaxy that particular spectral line is shifted by a certain amount. If we look at the change in wavelength divided by the actual wavelength, that will equal the speed of recession divided by the speed of light, which is z. Yeah, they give it a number z. And so sometimes an astrophysicist will just say it has a z of 0.3 or a z of 0.7 or something like that. Okay? But let's look at Hubble's law here for a second. V equals h over d. Notice that v is what we've graphed on the y-axis, the speed of recession, how fast the galaxies are moving away. D is our x-axis, how far away the galaxy is. So how are we going to calculate h? It's going to be the slope of the line, right? The slope of this line is h. It is an incredibly hard thing to measure, but it would be a great thing to measure. He thought it was around 500 megaparsecs per second or something like that. We now know, I think it's more down to around 70 or something, okay? So it is something that astrophysicists are trying to measure. And one of the reasons why it's helpful, I want you to see this for a second because I think it's pretty darn cool. One of the reasons why it's helpful is this. H is V over D, right? Wait, did I do that right? Yep. So 1 over H is D over V. But remember that V is just distance divided by time. So 1 over H is time. 1 over H, 1 over Hubble's constant is time. Time for what? The age of the universe. If we know Hubble's constant, we know the age of the universe, okay? Because 1 over Hubble's constant is the age of the universe. So if you can measure it, that's a good thing, because then we know how old the universe is. And currently, we believe the universe to be somewhere around 13.7 billion years old, okay? The problem with Hubble, when he did this, and his slope was about 500, 1 over h led to an age of the universe of about 2 billion years. And they knew that there was rocks on Earth that were 4.5 billion years old. And so he knew that the trend was right, but the slope was wrong, okay, in his data. Exactly. Brian. Here's Hubble's law. Okay. Here's Hubble's law, okay? So this happened right at the Great Depression. Things were going bad economically. Edwin Hubble was discovering earth-shattering things about the universe. And what he discovered is there's a relationship between the distance of an object and how fast it recedes. The equation is very simple. V equals hd. H is called Hubble's constant. Incredibly hard thing to measure, okay? It would be the slope of that plot we just looked at, of recessional velocity versus distance. And these are directly proportional. If you double the distance to an object, it's receding twice as fast. Currently, we think that h is somewhere around 75. You guys were saying, 65, 72. Was that what the book said, or was that? Okay. So there's a lot of uncertainty in these measurements. So it's in that range. When Hubble first did his measurements, he thought it was around 500. And like I said, we've gotten a lot more data since then. But if you know Hubble's constant, please remember this. If you know Hubble's constant, you can find the age of the universe, because 1 over h is the age of the universe. Okay? How does that work?